है इसकी ये उसके लिए होगा ना, उस ऑनलाइन उसके लिए। ठीक ठीक है, चल। So okay, we'll start this session. So in this particular sessions, we will cover the concept of hydrological modeling, and we'll see how we can develop that soil and water assessment tool that is particularly used for hydrological modeling, simulation, and all these things. So before going to particularly that SWAT models, we'll cover the basic things related to hydrological modelings. Like we should know what is the catchment and what are the characteristics of catchments. Okay, how means hydrological simulation models works, what types of equations they use. We will see all these things. So I think, and then we'll go for some kind of a case study, how you can incorporate the climatic data, what you have seen you have gone through that through the IPCC. You might have heard about that CMF 5 data or CMF 6 data. Have you heard that CMF 5-6 data? Coupled model integrated phase 5 model data, that GCM data, RCM data. So before using that data, or how we can incorporate these data in SWAT models, how we can develop that SWAT models or hydrological models, we'll see in this particularly in these lectures. So basically, what are the steps involved in SWAT modelings? We'll see what types of data is required, how we can prepare these data sets related to particularly SWAT models. Why we are using SWAT, we'll also discuss, and then we'll see one case study in which we have applied different GCM data, and then we have developed different scenarios, like you might have heard about RCP scenarios, reconcentration pathway scenarios. So we'll discuss during the case studies. So basically, first we'll see what is catchment. Can anybody tell me how do you define a catchment or a watershed or a basin? So I think you all of from hydrology or geology background, so you might have heard about the term related to catchment. So can anybody define me? What is catchment? Yeah, the land area which is draining to a particular the river systems or a channel systems at a particular locations, that is known as your watershed. Yeah, or basins or sub basins catchment. That we can means there is a not any hard and fast rules to call it as a watershed or sub catchments, but different country named its watershed or catchments like this. Or sometimes we may also define based upon the area. So as we are able to see this in this particular figures, whatever the rainfall which is taking place above this particular area, how much amount is going to collect at that particular outlet, that is the area is known as your catchment area, and that boundary which separates two adjacent areas is known as your ridge line. Okay, so whatever the amount of rainfall which are occurring in this particular area would be goes in two different directions. So some part of the rainfall will go and will takes flow in this particular area, and some part will go in the adjacent area. So every catchment is having some kind of a adjacent boundaries also. The ridge lines is the dividing lines of the catchments. Yeah, water divided lines we can say. And or we can also define it as a natural boundary, like you have an administrative boundary in a maps or on this district boundaries, state boundaries there. So watershed or the ridge line or the water divide line is the natural boundary, and this is the smallest unit where any hydrological models work. So at these level, like at watershed level, it computes all these types of your water balance equations. Whatever you have gone through in this particular course, you might have gone through that what are the water balance equations, how inflow and outflow is taking place within the catchments. You know about the water balance equations, the concept of water balance equations. Yeah, the mass inflow minus mass outflow, that is equal to change in the storage. And the inflow, whatever the inflow which we are getting, most of the times it is in the form of precipitations. Precipitation itself having so many means types, like in the form of snow we are getting, like in the form of rainfall we are getting, sometimes in the forms of hails, and some other forms is also there. So in different textbooks you will get all these types of informations. So at particular that catchment level, we are computing how much water we are getting and how much that water is converting into runoff, or how much water is converting into groundwater recharge, or how much water is going as a evapotranspiration or interception. The complete water budget equations will do at the catchment level only. Okay, so this is the basic unit where we start our things. So for that, doing all these things, we require some kind of a tools. Okay, so that tools is covered in a that hydrological models is known as hydrological models. So basically what we are doing, we are using some kind of a tools that is known as hydrological models. So basically they are the simplified representations of your physical phenomena. Okay, what they are doing, that basically hydrological models are doing, they are simplifying your physical phenomena with the help of some kind of a mathematical equations. Suppose that Manhattan campus, if you are taking the example of Manhattan campus, the boundary would represent as a ridge lines, and within that boundary how much rainfall we are getting, and the land use and the types of soils, how much they are converting or they are contributing, means to generating the runoff or evaporation or the storage, would be your means physical phenomena that is taking place within that closed boundary, and then how they are interacting with your land use and soils and all these things. So all these types of things we can capture with the help of some kind of a models. So they are simplifying our natural processes. Okay. Then the terms is simulations. So basically simulations is we can say as a copying or the mimic. They are mimicking means some kind of a natural processes. So whenever we do some kind of a modelings, we require to do some kind of a simulation with the help of some iterations and all these things. Then we have different types of models. We'll see that also. So basically that hydrological models are the combinations of equations, maps and the database. So as we discussed already, that hydrological models are the combinations of mathematical equations. Like you might have heard about y equal to mx plus c. It itself is a one kind of a models which gives you the slope of a line. You might have heard about the rational formula, that is q equal to CIA. Right? That is giving you the peak discharge values. Okay? Then by using that these kinds of mathematical equations, or sometimes we use, most of the times nowadays every hydrological models are working or using GIS as a platforms. So for that we produce some kind of a maps, and as well as we produce some kind of a database. For that we require some kind of a data. We'll see SWAT, in SWAT, particularly in SWAT model, there is a large number of data set is required. Okay, with the help of that, we also should know about the database management systems, about some kind of a Microsoft Access things we should know, because we have to do some kind of a database management things, because we have to create our own data sets if you want to build hydrological models for your study area and these things. And then the output which we will get in the form of maps, that georeference map or geospatial maps, that will capture the spatial variability within your catchments, like how much runoff is taking place or how much evaporations is taking place. You can spatially map those particular processes. So basically that hydrological models use mathematical equations, and then mathematical equations represent the processes. What are the processes are taking place? Like runoff is one of the process, evaporation is one of the process, groundwater recharge is one of the process, and that processes is captured by some kind of a parameters you have to use. That is your calibration parameter. We'll go step by step in that also. So that parameter, the understanding of that parameter is also very much important, because simply developing a hydrological model is not a very big task, but doing a calibration, it's very tricky task as well as the very tedious task, because unless otherwise means you don't have the complete knowledge of what processes are taking place in your catchment area, you won't be able to do the calibration part. So that is why you should understand what is hydrological models, what is hydrology, what is water balance equations, how. In the previous lectures, I am not going in details to water balance and all these things. I think they are already covered in this training program. So this is the one of the examples of your watershed models, like how we can create the catchment area or ridge lines. This is the examples of the upper lake of Bhopals. This is the Badbadra Dam and Kaliasot dams. These are the output locations. With the help of some kind of a GIS softwares, you can create these types of a watersheds or stream networks. You can compute the streams orders or the geomorphology of the complete geomorphology. What are the area of this particular catchment, the streams orders, stream length, how the tributaries are contributing to that. If you have that rainfall and land use and all types of other data, you can use in that data in particularly any models, not only in SWAT, in any models, or you can generate the statistics. So basically that hydrological models are divided into two parts. One is the deterministic approach, and then second one is the stochastic approach. So in deterministic approach, again it is divided into lumped and distributed. So can anybody tell me what is the lumped model or what is distributed model? Yeah. As a single unit. Can you give me the one of the example? Like you might have heard about the unit hydrographs, synthetic unit hydrographs. So they consider the complete catchment as a one unit. So they don't consider the spatial variability. So that is known as your lumped model. And what we do in distributed models, we divided the models into several parts. Like when we go to that SWAT particularly, that is also divide that catchments into sub-catchments, and then sub-catchments is further divided. We'll see that also. So that approach is known as your semi-distributed approach. Semi-distributed, I mean particularly SWAT. If we divide that particular catchments into a number of cells, that is the fully distributed approach. That is being used in WIC models or Mike SHE models. They use the fully distributed models. In that case, we have to predefine the cell size. Accordingly, it will compute what would be the cell size, what would be the number of sub-watershed and watersheds in this, but in your particular watershed. So at that particular level, it will compute the water balance or water budget equations for your catchment area. And then again, it will aggregate to the sub-basin scale and then to the basin scale. And then it will provide the average, basin average values. Means suppose you want to compute what is the average rainfall is your catchment is receiving. What are the average runoff your catchment is generating. So that distributed or semi-distributed approach is used. Then again it will divided based upon the types of flow. Steady flow, one is steady flow, you might have heard about in fluid mechanics books and all these things. Then another approach is stochastic models. So in that stochastic model, that is related to basically your climate model, GCMs, RCMs. They use the concept of probability as well as the randomness. How randomness means, because nature is very random, so we can't predict very accurately. That is why whenever we do some kind of a climate change modelings and all these things, I'll show also during my case study, we'll use 4, 5 or 5, 10 or 15 different types of GCMs, global climatic models or journal circulation models, we can say. We'll use different models because their inputs are different. So we are not able to identify which models is predicting well for our study area. So then we'll go for another technique that is known as your ensembling of the models, ensembling techniques. So we'll go that in your subsequent slides that also. So then the question comes, how do we select any types of models? Why we are interested in SWAT? Why not in HACK-HMS or WIC model or any other models? So can anybody tell me? So what are the criteria to choose the particular models? Why we are not doing on HACK-HMS? Because simply HACRAS or HACK-HMS is also a model which are used for rainfall runoff modeling. Okay. We can say event-based models or purpose also. Yeah. What you are saying? Depends upon parameters, depends upon expertise, depends upon data, depends upon the requirements. And then why we are using SWAT? Because that HECRAS, Mike SHE, all these are the means event-based models, or they are generating some kind of a runoff. But the advantage of this SWAT model is these are based on your management practices also. You can incorporate different types of management practices which are taking place in your particular catchment area, like what are the irrigation cropping patterns you are using, what types of irrigation patterns you are using, what types of land management practices are being used in your catchment area. You can give input in your SWAT model also. So that is the basic requirements. That depends upon what types of studies you are going to do. And while doing these types of studies, we should know some catchment characteristics, like what are the topography, what are the shape of the catchment, size of the catchment, then land use of the catchment. Why? Because they all are governed the runoff characteristics, or as well as the runoff volume. How topography would that cover the runoff characteristics? Because wherever you get the steep slope, you will get the means more runoff generation, or the lag times, your time of concentration would be less. Then again, shape is also would be one of the major factors which contributes in runoff volume generation, the quantitative size. Similarly, then the soil types. Again, the runoff characteristics would majorly depends upon the type of soils. Like if you have gone through that any engineering hydrology books or hydrology related books, they have divided that 4 types of hydrological soil groups is there. That is A, B, C, D. So how they have classified that A, B, C, D group? Which type of soil would give you the more runoff or less that infiltration? Yeah, okay. So let's talk about the type soil, hydrological soil group which is having that group A. So it will generate more runoff, or infiltration capacity would be the more runoff. Or what about the hydrological soil group D? Yeah, so curve number is one of the parameters. That SCS curve number equations, you might have heard about that SCS curve number methods, in which that is also used in SWAT model also. One equation is also there, that is known as your green-amped equations. That is also being used. Provided for the green and amped equations, we required hourly data or sub-hourly data. For SCS curve number equations, we will use the only daily rainfall data and all this thing. So these are the some parameters which we have to incorporate, or these becomes the input parameters for your hydrological models. Like types of land use is also affect your runoff generation quantity as well as the quality. Suppose if you are using some kind of a means models in your urban catchment area, so in that case particularly SWAT model might not work as well as it will work in a agricultural catchment area. So basically SWAT model is developed for agricultural catchment area only. So for urban catchments and or for to simulate the urban storm hydrology, will go SWAT, or some another kind of model is there, or some kind of means you can use empirical equations that is developed for regional scale, like rational formula. So all the design parameters which is used in your sewerage designs or pipeline network, that is based on your rational formula only. That they compute the peak discharge values during the monsoon season and all like this. So these are the some parameters which we have to keep in mind while doing the modeling parts. So this is your complete hydrological cycles which might you have seen. So as precipitations or rainfall taking place, so once the your infiltrations that requirement is fulfilled, then the surface runoff will take place. From that surface runoff, you all know that evapotranspiration will take place. Then during that your infiltration parts, it will go deeper and takes part into the groundwater recharge. That groundwater becomes your base flow, and then base flow again contribute to your surface runoff. Based on that, we divide our rivers into perennial or non-perennial rivers. You might have heard about the perennial rivers, non-perennial rivers. You know how that perennial rivers are getting water? Through the base flow only, throughout the years. Yeah, in perennial rivers we are getting water throughout the years. The main source of the waters for the perennials is the base flow. Okay, then some kind of a losses is also there interception losses is also there, transmission losses is also there. So all types of this water balance we can compute in a software, or in today's tutorials, by the end of this lectures or the tutorials, we will compute the complete this hydrological cycle for our basin soils. Whatever we are seeing in this will show in that particularly numerical values. It's like if we are getting 1000 mm of rainfall, how much rainfall is converting into runoff, how much that 1000 mm of rainfall is converting into groundwater recharge, or like that will show you. So while doing that particularly modeling parts, so some general procedure is there. We'll quickly go through that, and then we'll start the requirement of SWAT model and all these things. So the very first step is that identifications of information required for management decisions and all these things. What types of data you have, or what type of modelings you want to do. Like suppose in case of groundwater modelings, if you want to do, so you have to acquire the knowledge about the what are the groundwater wells is there, what are their depth is there, and what are the other parameters like types of soil is there, land use land cover, what types of land use land coverage exist there, or the hydraulic conductivity of the wells and the soils and all these things. Then you have to develop some kind of a conceptual models also. That is based on your experience, or what types of mathematical equations you are going to use. What are the physicals process are taking place within your catchment area. Based upon that, you can use the already developed mathematical models and like that. And then you have to define some kind of a boundary conditions or input data and all these things. Then we'll go for model development. Then once you have collected, you have established what types of mathematical equations you are going to use, or what types of data you are going to use, then you can go for model development phase. And then once you have developed, then you have to check the outputs in the form of what types of output you are getting. You have to match that output with your observed data. Like as we have seen the catchment boundary and all these things, catchment definitions, and then we have defined that at a particular outlet point. So sometimes in that particularly catchment outlet points, we have some kind of a measuring devices or measuring techniques is there. Like in India, that Central Water Commissions is doing. In the first lecture, they have mentioned Aditya sir. They are monitoring the discharge, and that particular location within that catchment is known as your gauge catchment. Ungauged catchment is also there. For that ungauged catchment, they won't measure. Some kind of a weird or some kind of advanced techniques is also there for measuring the discharge and all these things. So once you have developed your models, you have got that output, then you have to match that output with your observed data, and then you have to compute some kind of a statistics. That is known as your model calibration. So basically what you are doing, so you are trying to match whether your predicted or simulated output is near to your observed output or not. You have to basically you are trying to figure out the difference, what type of difference you are getting. Like that, you have to plot these types of hydrographs between your observed and simulated data. So you might have seen all these types of graphs in your research paper. Okay? This is your discharge, this is versus your time curve. So you have to, suppose this is your observed data, or this is your simulated data. So you have to identify what type of gaps you are getting, or is kind of a shifting is there, like that. And then you have to compute some kind of a statistics in the form of R square, in the form of net Shetcliffe efficiency or percentage bias. Like that you have to compute, and then you have to compute the model performance. If your model is performing satisfactory, then you can fix your parameter. Otherwise, you have to adjust your parameters. That process is your model calibration process. So that is one of the most tricky part. That is why you require the complete knowledge of hydrology. Otherwise, you won't be able to do calibrations. If you don't know about the curve number methods, then how would you identify? Curve number is the functions or dependent upon the land use as well as the soil types and the management practices, whatever management practices is taking place in your catchment area. So you must know the hydrology as well as the your catchment areas also. Then if you talk about some kind of evaporation equations, there are 3 equations there in SWAT model also. Like you might have heard about that Penman-Montath equations. So that Penman-Montath equation requires huge number of data. Every climatic data, whatever you have heard, would be used in Penman-Montath equations, like solar radiation, wind speed, wind velocity, relative humidity, solar radiations, everything is required. So it's a very very complicated equations we can say. Then the second is Priestley-Taylor equations. Some parameters have been omitted from that equations. So some less parameter is required for Priestley-Taylor equation. Then the third one is Hurgewes equations. In that equations you requires only solar radiations values or minimum maximum temperatures. Based on that solar radiation and minimum maximum temperature values only, it will give the evaporations values. So like that, if you have the knowledge of hydrology, then only you will be able to do such kind of analysis. So all these equations having some kind of a coefficients. That coefficients is your parameters, which you need to adjust during your calibration parts. Okay, and all these coefficients having some kind of a values, minimum values as well as the maximum values. Like if we talk about curve number, that curve number itself having some kind of values that is varying from 0 to 100. 100 means completely paved area. Your means rainfall directly converted into the runoff, like that. So if you have 70, 30, in K. Subramanya, they have given the complete table for that curve number with their possible range as well as the land use type and the soil types also. So in engineering hydrology book. So like that we have to understood the groundwater parameters also. So in particularly SWAT model, there are around 50 parameters there for your discharge calibration. If you are working in snow feed watersheds, then you have to incorporate the snow parameters also. Like what is the lapse rate, how temperature is varying, what is the snow means what percentage of rainfall is getting in the form of snow, like that. All these types of inputs we have to give. So that requires very extensive means knowledge about hydrology as well as the catchment characteristics. Once you have done that calibrations, basically in calibration what you are doing, we are doing some kind of a trial and error or some kind of a fine tuning. We are trying to match our observed data graph with simulated data graph. The ultimate goal of calibration is this. Once we satisfied, what happened in this case particularly, we don't bother about the actual hydrology or actual processes. We just focus on that we have to match this observed and simulated. So we every time, most of the times the students do over calibrations. So they are getting very good results during the calibration periods. Once they go for validation periods, they are not getting good statistics. So there are some values already defined for these statistics. We'll go through that also. So once you are satisfied with that statistics, you stop your calibration and then you go for validation parts. So during validations, what we have to do, we have to give some kind of a unseen data. So like when we do some kind of a calibration and validation techniques, then we have to divide our data sets. Suppose you are running your models from 1960 to 2024. So then you divide your data sets, some parts around 60% you keep for your calibration part and 40% you keep for your validations part. So like that we have to do some kind of a calibration and validations. So once you fix your parameters and then you provide some kind of unseen data to your models, and then again you have to compute the statistics, whether these statistics are coming within the range or not. So then only you decide, okay, my model is giving satisfactory results. Now I stopping the calibration and validation part have been done. Then you go for scenario generations. Okay, then we will use some kind of a GCM, general circulation or general climatic models. Their output will use, then we'll go for predictions. Like I'll show in my case study, we have predicted till the end of this century, like 2100. So we have divided all this data range into 3 parts: near future, mid future, far future, like that. Then we have to see what are the changes has been taken place during the by the end of the century within my catchment area, like that. So this is the overall pictures, like that we have to do. Then one terms is also there, the uncertainty analysis. This is one of the most important part we have to do again in hydrological modelings. So we'll see during that model validation and all these things. Then we'll go for scenario generation, then model uncertainty analysis, then report writing, conclusions, and all these things. So this is the overall steps which you should use during your modeling part. Whatever models you are using, these are the common steps. In every models we have to follow these steps. Then some limitations would always be there, like you won't be able to capture the complete phenomena, like some models won't be able to capture the peaks, some models won't be able to capture the base flow phenomena and all these things, depending upon their data limitations and other requirements. So these are the some major hydrological models you might have heard about that. Hydrological simulation programs, Fortran, HPHS models, then HECRAS models you might have heard, Mike models you have heard, and then soil and water assessment model is there. So these all are given model types, their parameters with lumped, distributed, and all these things, continuous models. So basically we are interested in SWAT model, so we'll discuss only SWAT model only. So now come to the SWAT model. So basically SWAT model is a continuous models, physically based, semi-distributed. By mistaken I have written distributed, it is semi-distributed. Okay, then process based model, physically based models, then that simulates the management practices, as I said. Why SWAT is different from any other hydrological model? Because of this, because it simulates the management practices also, provided you should have the knowledge where and how to give that management practices in the particular SWAT model. Otherwise, simply you might have done that previous exercise in rainfall runoff modeling, some kind of regression equations you have used, or you have directly generated runoff using the rainfall data and in these things. Even in your ANN modelings also, they are known as your black box models. You just have to provide some kind of rainfall data, and you have to provide some kind of rules, and based on that rules it will automatically create runoff, and it will create some kind of statistics and all these things. But in this particularly models, we have to provide land use informations, soil type informations, slope informations, as well as the weather data. So whatever processes are taking place within our catchment, we have to provide all the information to this particular models. That is why it is being used, or one of the most widely used software in the field of hydrology. The another reason is freely available. You don't require to purchase its license versions, or if you are working on QSAT or QGIS, that is completely free, so anyone can use. So like that, what it can simulate the hydrology of the basins, like that, whatever precipitations or rainfall taking place within catchments, how it is going to convert into runoff, evapotranspirations, or storage, groundwater recharge, like that. It will also do the stream routing. It will use the Muskingum method or variable coefficients methods for your stream routings. Then sediment erosion is also taking place within the catchments, can be captured by SWAT model. Then for that sedimentations computations, it will use universal soil loss equations. You might have heard that modified universal soil loss equation would be used in SWAT models. Then somebody is interested in plant growth or nutrient pesticide cycles, agriculture management practices, if they have the data related to crop management, what type of irrigations, what type of crops are growing in your catchment area, what type of irrigation practices is there, they can be incorporated in SWAT model as an input, or will get the output like that. So these are the ultimate output of SWAT models. Okay, so now come to the working methodology of SWAT, how SWAT model works. So basically SWAT requires 4 types of inputs. 4 types of input is required by SWAT model. That is the very first input is your DEM data, that is your digital elevation data. You will get all these types of data, mostly data from the remote sensing. So yeah, so for that you can use SRTM data, you might have heard about that, or you can use some kind of a ASTA data, or you can use that Cartoset data. They both are from USGS you can get, or you can get from Bunidhi. Then the second input you require, that is your LULC information, that is land use land cover change information, or land use land cover informations you require. So with the help of again GIS softwares and remote sensing data, you can create that LULC. If you don't want to create, I'll show the links and some kind of inputs you can create. Then the third information you require is your soil data informations. Okay, so what you can do, you can directly use the soil map that is prepared by FAO, Food and Agriculture Organization USA. They are providing the raster image of that particular for the complete world soil data is there. With the help of that you can create your own soil database. But yeah, that is the one problem, and second problem is that that is available at a very coarse resolutions. So in that case you can do, for your initial model building or to understand how your model works, you can use. And once you get some kind of a confidence how to develop that models or how to run that models, you can go for NBSS LUP maps, National Bureau of Soil Survey and Land Use Planning. They are providing hard copy maps. You have to digitize that maps, and then along that maps you will get some kind of a booklets. From that booklets, some manual types of books you will get. From that manuals you have to extract the soil properties, like what are the soil types is there, what are the hydraulic soil group is there, what are the number of layers they have incorporated, what are the hydraulic conductivity, what are the anion information, cation information, what are the information required by SWAT database. You have to prepare your own database. That is the only way. Otherwise you can, if your catchment area is small, you can go into the field or you can collect some kind of a soil samples. Or some readily available tools is also there, like soil pseudo functions, one software is also is there. If you have some samples within your catchments, you can give to that samples to that particular software, or they will generate with the help of interpolation techniques and other techniques. They will generate some kind of a statistics or some kind of a properties, soil properties, other properties related to your water catchment area. So these are the third input. The fourth input you required is your weather data. So in weather data, mostly you require that rainfall data, temperature data, or your wind speed, solar radiation, relative humidity. If you don't have wind speed, solar radiation, relative humidity data, only rainfall data and minimum maximum temperature of the day is sufficient to generate or to simulate the hydrology of your catchment area within SWAT models. Okay, so you have to keep in mind that at least rainfall or temperature data you should have. Rainfall data in the form of daily data and temperature data in daily data, maximum minimum temperature of your daily rain data. Then other data you required, that is your observed data. Observed data, like if you are computing, you are observing, means that the statistics of between observed and simulated data with the help of discharge data. So in that case your observed data would be discharged. You can compute your model output with the help of evapotranspiration data also, or some kind of a satellite is there, GRACE satellite you might have heard. They are also providing some kind of a soil moisture data readily available. So if you have soil moisture data or evapotranspiration data or some kind of a groundwater data, so you can do calibration with the help of these observed data also. Yeah, sediment concentration data can also be there. So then in that case you have to, if you are interested in sediment concentration, then the SWAT is also providing sediment concentrations also in gram per liters, or shayad in mm gram per liter is their unit, yeah. Or if you are interested in load, then you have to convert your observed data into load. You have to multiply it with velocity, and some kind of a coefficient is there that concentration data would be converted into load. So these 5 types of data you required. So basically from digital elevation models, it will compute the slope, and then based on the slope, it will compute some kind of a flow direction, flow accumulation. Then ultimately it will create the basin boundary, and then that basin boundary would be further divided into sub-basins. Okay. Then from LULC map, then it will use the LULC map, then the soil map, and then basin boundary. Again, it will means that break your sub-basins into some kind of a smaller units. That smaller unit in SWAT, that is known as your hydrological response unit. This is the smallest unit at the particular that SWAT model work. Okay, so that at this level, at HRU level, it computes some kind of a water balance. For that, it requires some kind of a climatic data. Climatic data, as we discussed, in the form of rainfall or temperature data it will use. Then it will compute the water balance equations for at a particular HRU. At a single HRU, it will compute the water balance equation, that what are the inflows taking place in that particular HRU, what are the outflows taking place, and what storage is taking place in that particular HRU, it will compute. And then again it will aggregate all these HRUs at the sub-basin level, and then it will aggregate to the basin level, and then it will give the output, as I have shown in the previous slides. Whatever the precipitation is taking place, or what are the precipitation is converted into rainfall or runoff, and like that. Then we have to run the model. So these are the steps. The first step is we have to create the, this is the first steps, basin, sub-basin. Then the second step is the create HRU. Then the third step is the means we have to run the model, and then we have to identify that calibration and validation parts we have to do. During that, after running that models, I'll show you that that module is there, edit SWAT output. In that particular edit SWAT output, we have to provide the management practices. What type of management practices is taking place, or if we want to do, if we are interested in reservoir modelings, we can incorporate here in these terms. Once we satisfied with that, all these input parameters, all this are working well, and we'll go for run model, and then we'll go for calibration and validations. For that, one terms is also there, sensitivity analysis. As I have already mentioned that for discharge calibrations, we have around 50 parameters. So all the 50 parameters might not be useful for our calibration purpose. So we have to reduce these parameters, so we can do some kind of a sensitivity analysis. So again, there are different types of methods is there doing sensitivity analysis, or for that calibration, sensitivity analysis and validations, there are stand-alone software is there that is known as your SWAT CUP, calibration and uncertainty program. So once we have completed these types of steps within that SWAT models, we bring that output of SWAT model into the SWAT CUP, and we'll do calibration, validation, and all these things. And then once we satisfied with that, we'll stop the output, and then we can go for scenario generation, or we'll use the GCM, RCM outputs and all these things, or we can do predictions like that. So this is the simplest methodology I have presented, but it is not as simple as it is looking. So this is the water balance equations which is being used by SWAT models. Basically, this is your input, or these all are output. This is your precipitations, this is your runoff, evapotranspiration, groundwater recharge, and change in storage. So basically, this equation is being used in your SWAT models. Then SWAT is basically a combination of multiple models. As we have already discussed, that hydrological models are the simplification versions which we are using, and these are the combinations of mathematical equations. So SWAT itself is a combination of different types of sub-models. Like I have already mentioned, it uses SCS curve number method for your runoff computations. We are not going into details because all these details are already given in your textbooks and all these things. You can refer directly, or even SWAT manual also. All this information is given. I'll show that on SWAT website also. Everything is available. Then it will use the Muskingum routing methods for your river routing. Then Penman-Montet equation, Priestley-Taylor equation, Hurwitz equation, all the three options is available. You can choose any one depending upon your data, what type of data you have. You can choose any method for evapotranspiration computation. Then for sediment computations, it will use modified universal soil loss equation. That universal soil loss equation you might have heard that each and every parameters represent some kind of a layer, RK, SL, CP. So with the help of that, it will compute the sediment loads. So these are the GIS layers which you have to create before entering into the SWAT environment. Like we have to create the download these digital elevation models that is available with the help of remote sensing images like SRTM, ASTER, Cartosat. Nowadays we are using ALOS Pulsar. They are all are available at different resolutions, 30 meter, 12.5 meters, or SRTM is also available at 90 meter resolutions. That is, I am talking about horizontal resolutions. We have to see the vertical resolutions also while doing that these types of modeling. Then the second input is your land use land cover maps. As I have mentioned, we have to create again for land use land cover maps. We have Landsat satellite data, or LIS sensor is also available. Landsat is your US satellite data, or LIS is resource set data that is developed by NRSC. This Indian satellite data is there, resource set. LIS 3, LIS 4 data is also available. LIS 4 data is available at around 5 meter resolution. So if you have not gone through that, so you can go through that or you can download. Then the soil map. If you have some kind of NBSS LUP maps or hard copy maps, you can digitize, you can create your own data. Otherwise, you can use the FAO soil database also. So for this example, I have used FAO soil database, and then again, you have to use the climatic data. If you have station data, that is well and good. If you don't have station data, then you can go for gridded data. IMD is also providing gridded data. Even if we use that GCM data, that is general circulation models or general global climatic models, that is also available at grid. So I'll show you that also. So we have already discussed the climatic data which we require. Then we have also discussed this. So this is the ultimate output of the SWAT output, which we will get in the form of complete water balance equations. We have already discussed. So like I have already told you that after completing that model run and all these things, we have to do some kind of a sensitivity analysis to reduce the number of parameters. So if we are using some kind of a software like SWAT Cup, that is calibration and uncertainty programs, in that particular softwares will get the two types of methods, that global sensitivity analysis or that one at a time sensitivity analysis. So basically in sensitivity analysis, we are trying to identify which parameters are more sensitive to our catchments. Like if, as I have already told, that each and every parameter is having some kind of a range or some kind of a values, like curve number is varying from 0 to 100. Once we are varying with curve number or its value, and then we have to again rerun the model and we have to check the output. If we are getting some different type of output, then that particular parameter would be the sensitive parameters. So it is the nothing means we can say it's a rate of change of output with respect to input. How we are changing that input parameters or how our output is changing with respect to that inputs. So that particular thing is known as your sensitivity analysis. There are two methods, global sensitivity analysis. In that particular methods, what we do, we provide all the parameters. Like if we are talking about discharge parameters like 30-40 parameters, we can give all the parameters, and we use some kind of a statistical method like T-state methods or T-student method or P-state method is there. With the help of that, it will compute. Some optimization techniques is also there. Then it will give what parameters is sensitive to your parameters watershed. Then in one at a time, we have to give one parameter at a time, and we have to rerun the model several times, and then we have to check whether our output is changing or not, depending upon that. So this is the time consuming methods, or global sensitivity analysis is less time consuming as compared to one at a time. It depends. Sensitivity analysis में simulation का कोई role नहीं है. नहीं, वो डिपेंड करता है, इट डिपेंड्स अपॉन द नंबर ऑफ पैरामीटर्स ऑल्सो. यू हैव टू गिव एटलीस्ट 7, 8, 10 पैरामीटर्स. इफ यू आर गिविंग 2, 3 पैरामीटर्स, देन इट वोंट चेंज. एटलीस्ट यू हैव टू गिव 10, 20 पैरामीटर्स. देन यू विल गेट द that global sensitivity analysis may p test or t state values you will get. You have to increase the number of parameters in single. हाँ, नहीं ऐसा नहीं होगा. हाँ, वो डिपेंड करता है. अगर आपने बहुत सारे इटरेशन ऑलरेडी कर दिए हैं तो फिर चेंज कहाँ से होगा. वो पी फैक्टर आर फैक्टर आपके आता है बेसिकली अनसर्टेनिटी एस्टिमेशंस के लिए. मतलब जो डेटा विच वी आर प्रोवाइडिंग इन ए फॉर्म ऑफ लाइक वी हैव टू प्रोवाइड इनपुट डेटा मीन्स ऑब्जर्व्ड डेटा. ठीक है, तो व्हाट परसेंटेज डेटा 25 पीपीयू प्लॉट्स भी आता है आपके पास, है ना. तो कितना परसेंटेज डेटा वो पर्टिकुलर सॉफ्टवेयर कैप्चर कर रहा है. सारे के सारे आपने लेट्स से 100 पॉइंट्स दिए, 100 पॉइंट्स वो कैप्चर नहीं कर पा रहा है. वो दैट इज द पी वैल्यू एंड आर वैल्यू. ठीक है, इसीलिए अपने को क्या होता है, अगेन पी फैक्टर आर फैक्टर्स भी देखने रहते हैं. सिंस ये इनिशियल स्टेज थी इसलिए मैंने इस पर ज़्यादा फोकस नहीं किया, बट अभी हम मॉडल रन करेंगे तो आई विल शो यू दैट. हाँ, बिल्कुल बिल्कुल, अगर आप इस पे ध्यान नहीं दे तो. बट लेकिन स्टैंडर्ड प्रैक्टिस इज देयर, यू शुड लुक इनटू पी फैक्टर आर फैक्टर आल्सो रादर देन आर स्क्वायर एन एस ई. और बेसिकली व्हाट वी डू, वी फोकस ऑन आर स्क्वायर एन एस ई ओनली. दैट इज द रॉन्ग प्रैक्टिस. मैं आर श्रीनिवासन सर से मिला हूँ, करीम अब्बास सर से भी मिला हूँ. they are the developer of SWAT, so they also said the same things, because we look p factor and r factor, we don't look r square and SE and pi bias. वो डिपेंड करता है. इफ यू आर रनिंग ऑन डेली स्केल देन 0.5 इज मोर देन सफिशिएंट. यू कैन गो फॉर मीन्स प्रिडिक्शन एंड ऑल दिस थिंग्स. इफ यू आर रनिंग ऑन मंथली स्केल देन 0.6 इज सफिशिएंट, है ना, कोई इशू नहीं. हाँ बिल्कुल, ओवर सिमुलेशन, उसमें ओवर कैलिब्रेशन हो जाता है, सही बात है. उस केस में आपको क्या करना है, देन यू हैव टू, आपको क्या करना है, डेटा सेट्स को बाहर लेके आना है. फर्स्ट आपको आइडेंटिफाई करना है विदाउट गोइंग इनटू द स्वैट कैप एंड ऑल दिस थिंग्स, एक्सेल के अंदर ही, कि हाउ योर डेटा इज परफॉर्मिंग ऑब्जर्व वर्सेस सिमुलेटेड. उसमें आर स्क्वायर अभी कितना आ रहा है ना. देन आपको एक पेपर दूंगा मैं अभी, देन यू करीम अब्बास का ही है वो पेपर, है ना. दैट एंटायर यूरोप की उन्होंने वो हाइड्रोलॉजिकल मॉडलिंग करी है. देखा आपने वो पेपर, कॉन्टिनेंटल स्केल हाइड्रोलॉजिकल मॉडलिंग ऑफ द एंटायर यूरोप. इन दैट पर्टिकुलर पेपर दे हैव मेंशंस व्हिच दे हैव मेंशन सम काइंड ऑफ ए प्रोटोकॉल. इफ यू आर गेटिंग योर ऑब्जर्व्ड और सिमुलेटेड वैल्यूज ग्राफ, लाइन ग्राफ, if you are shifting or your peaks are not matching, then which type of parameters you have to adjust. You don't have to adjust all the 50 parameters. ठीक है, मैं अभी इसमें दिखाई देता हूँ, शायद मेरे पास होगा वो. So if you want, I'll share you this paper. So in that paper they have mentioned continental scale hydrology and water quality model for Europe. So that was the postdoctorate paper of Karim Abbas sir. They have developed. Yeah. So if you are getting these types of case, then in that case you have to adjust only these parameters. Means this, you have to increase the curve number, you have to decrease the soil available water content. Again you have to decrease the soil evaporation compensation factor, groundwater recharge, you have to increase like that. If you are getting these types of pictures, means results, so that is why I am saying before going to SWAT cup you have to analyze your data in Excel only. Then you can easily identify which type of parameters you have to adjust. So that is the means best paper which you can refer, or which you can do for calibration and all these things like that. So all the scenarios is given, whether you have to increase the curve number or soil water contents or ESCO, HRU sleep, curve, Manning signs, overland flow and everything. Again, they have also talked about P factor and R factors also in this field. बिल्कुल बिल्कुल नहीं, ये दैट इज द वन ऑफ द लिमिटेशंस ऑफ स्वैट के पीक इसमें थोड़ा मैच नहीं करता है. ऑब्वियसली ऑब्वियसली एनएस वैल्यू वो डिस्चार्ज की उस पर ही डिपेंड करता है ज़्यादातर. हाँ 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 हाँ, उस केस में फिर हम क्या करते हैं, ओवर कैलिब्रेशन करने लग जाता है. अदरवाइज आप अगर डेली स्केल पे कर रहे हैं, इफ यू आर गेटिंग 0.6 दैट इज मोर देन सफिशिएंट. मंथली स्केल में 0.65 0.7 भी है तो मोर देन सफिशिएंट है. हाँ, पूरा ये टेबल है. ये अभी आपके ये मैं बता रहा था, ये दिस इज द टेबल विच इज गिवन बाय मोरेशी इट ऑल. ठीक है, इफ यू आर गेटिंग आर स्क्वायर एंड एस ई पी बाइस वैल्यू विद इन दैट रेंज देन ओनली योर मॉडल विल बी satisfactory. ये this is values are given for discharge. For sediment these are at some upper side, and they have increases some kind of a p-bias values for sediment also, because calibration of sediment is not a easy task. Okay, so these are the statics which we are interested. Other than these statics, some BR square or some other parameter is also there. Culling-Gupta efficiency, some other parameters is also there. So now if we talk about that application of SWAT, so we can determine the hydrology as we have already discussed. We can compute the transportation, sediment transportation, nutrient, pesticide. We can do the water quality analysis also, like phosphorus, nutrient, all these things we can do. Then we can do some kind of a climate change analysis, even land use, land cover change analysis. If you have temporal data of your study area, how land use changes are taking place, you can incorporate these changes in your model. Or the climatic data if you have, so you can incorporate these data also. So as I have mentioned that data sources, so 4 types of data is required, 5 types of data. So from where you can get, so I think you all know, you can get the DM data from Bhunidhi portals. Bhuvan portal is not working nowadays, so Bhunidhi portal is there. From there you can get the Cartoset data as well as the list 4 data. Even Sentinel data you can get at 10 or 20 meters, or list 4 data you can get at 5 meter resolutions, or you will get the Cartoset data. For SRTM or ASTA data you have to use USGS. They will provide the GeoTIFF format, raster data format data. So that becomes the input for your SWAT model. So first you have to create login and all this thing. The second portal is USGS. From here you will get the SRTM data or ASTA data, digital elevation data, as well as the Landsat data. Landsat data that is starting from 1975 to till today. From Landsat 1 to Landsat 9 data is presently running. You will get all these data sets. If you do some kind of a land use, land cover change analysis, you can do. Then that Landsat data is available at 30 meter resolutions. If you want some kind of a fine resolution data, you can go for Sentinel data that is available at 10 meters. Okay, that from Alaska satellite web portals. So these types of inputs we have already discussed. Then if you don't want to create your own land use map, then ISRI has provided Sentinel-2 data at 10 meter. They have directly give you the land use, land cover maps for the entire world. Okay, then other sources is also there. Global irrigated area maps is there. Moody's land cover maps is there, but they are available at very coarse resolution. So better you can use that Sentinel data that is provided by ISRI. Then even Bhuvan also you will get some kind of a classified maps, but that is in the form of JPEG image. You have to geo-reference that images. They are not geo-referenced, so you can't readily use that data. So now this is the, yeah. So if you want to download that ISRI data, you will get window like that. From that window you have to download the data. 2017 to 2024 data is available for the complete world at 10 meter resolution. They have classified maps, land use, land cover maps you can directly get. Then other maps is also there. Global irrigated area maps that is available around 5 meter resolutions. Then those who want to do some kind of a temporal analysis, they can follow this link, or from that you will get the 1985, 1995, 2005 data sets for the complete India. Okay, that is made on Landsat data. Then Modi's data is also available. So like that you can create your own land use land cover map with the help of Landsat or Sentinel data. So these are some examples. Then from FAO you can get the soil map, or the alternate is this National Bureau of Soil Survey and Land Use Planning maps. From this you can get the soil maps. So this is the link for your soil map. You will get the download options here. So along the data you will get the raster file as well as the database. So while doing some kind of a modelings, you have to integrate that database with your raster image. Okay, so you should know some basics of GIS also. If you want to digitize some kind of a watershed boundary and all these things, so Survey of India is also providing topo sheets. Just you have to register on that Survey of India portals, and you can download the topo sheets of your study area for your land use land cover accuracy assessment. This is the FAO map, and this is the map which I have created from NBSS LUP maps. So you can clearly see in FAO I was getting only 4 soil classes, while in NBSS LUP around 50 classes I was getting. Okay, and then I have also created the database in Excel, and then I have merged that database with that raster, because both Excel database as well as the raster image is required in SWAT modeling. Then the climatic data you can get from IMD. Then global weather data is also available from SWAT website. Or if you are interested in CMIP 5 data or CMIP 6 data, you can go for web portal is developed by Professor Vimal Mishra, if you might have heard. Professor Vimal Mishra from IIT Gandhinagar, they have developed a web portal for all the Indian river basins, in which they have provided the SSP scenarios data. CMIP 5 data would give you the RCP scenario, reconcentration pathway scenarios. Okay, and now the research community is using you might have heard about in IPCC lectures, that CMIP 6 data is currently we are using. They are providing SSP, socio-economic pathway scenarios. So just you refer that paper. You all know that you can get the IMD data from IMD websites. They are providing rainfall data, daily rainfall data at 0.25 degree by 0.25 degree net CDF files. You have to convert that net CDF file into CSV format and all these things. I'll show you how to what type of format is required in SWAT. Then global weather data from SWAT website, you can download that data. Then for CMIP 6 data, you just go through this paper. In this paper, they have provided the link. Following that links, you will get the complete data, CMIP 6 data for your entire Indian river basins. Like I have downloaded for my study area. So there are around 13 SSP scenarios, 13 GCMs data is available for different SSP scenarios. Historical data is also there, then future climatic data is also there. From 2011 to till the end of the century, 2100, they have provided all this data for the entire river basins. 13 models, 13 GCMs data is there. मैं भी data भी show करता था. Yeah, they have already did that bias correction and everything, so you can directly use it. First, you have to match once. You have to cite their paper, or you have to acknowledge. Yeah, you have to just give that reference from their paper also. So for our study, which I'll show you, we have used only 5 GCM data, and that is most suitable for Indian regions, and that is that conclusion is given by Suvimal Ghosh, Professor Suvimal Ghosh. Based on that papers, we have chosen 5 climatic data only. Yeah. Yeah, you can choose. Yeah, you can choose all the 13 models, or even some models are not performing well, you can omit that models. That is the basic criteria you can use. So then if you want to directly use the SWAT models, so from that particular source you can get the entire India data sets for the complete India in the SWAT format only. The land use maps, soil maps, everything you will get in the SWAT formats. And then for that you require some kind of observed data. So water resource information systems, that is known as your India Varis systems, is there. I think they are updating their websites. So nowadays you might not be able to download some kind of observed data. Otherwise, for classified river basins, you will get all the data. Classified means that are not sharing the international boundaries. India has divided their river basins into two systems, classified and non-classified. That Ganga, Indus, and all this, which Brahmaputra, they are sharing international boundaries, so it is difficult to get that data. But otherwise, for southern Indian regions like Tapi, Narmada, Krishna, Godavari, you will get all this data on India Varis websites. So this is the portals from which you can get the data. So once you have identify the models, you have collected some kind of input data, you have prepared the inputs, everything is ready, or you have done models, you have done calibration and all these things. Now you are ready for scenario generation. Okay, so till now with what we have done, we have created some kind of a base model with the help of historical data. Historical data means we have used DM data, we have used IMD data. Till today we have available whatever data from 19012 2024 and all these things. And then we have completed the calibration and all these things. Once we have satisfied with our models, we can use the GCM data with our calibrated models. So for this particular study, we have used 5 GCM data that is being given us to that regional climatic projections in India with a statistical downscaling. This is the portals from which you can download the CMIP 5 data. They are providing RCP 4.5 or RCP 8.5 data. For 5 GCM data they are providing. I'll show you that 5 GCM. And then we have used the readily available NRSC land use land cover map that is available at 56 meter resolutions. We have created that NBSS LUP soil map. We have used 30 meter DM data, and the resolutions of GCM data was 0.25 degree by 0.25 degree. Then we have used the observed discharge data. So this is the GIS representations of my study area. Like that we have created. Okay. Then we have done all kind of simulations on all these things at daily scales. We have created at 2 stations was there, gauging station. One is Burhanpur, second one is your Hatnur. Hatnur was our dam. So whatever inflow we are getting, we have to provide as a outflow to some other catchment area also. So like that we have computed at daily scales. These are the P factor, R factor values which we are talking about. And then this percentage statistics we have also computed. We have computed that basin scale values. All will do in that next tutorial part also. So this is the basic picture which we got in the form of that water balance equations, and these are the different models which we have used. That is BNU and CCMA, that is Beijing National University model, and the second one is Canadian model, and the third one is German model, that is Max Planck Institute lower resolutions models. So these 5 models for 2 different scenarios, RCP scenario, reconcentration pathway scenario is there, that is based on the carbon emissions. That 4.5 is the scenario, is the moderate scenario, 8.5 is the worst scenario. So we have got these types of complete hydrology. So what we have concluded in this study, that actually I am not showing all the results because we are under review. My paper, one of my paper is under review, so I am not able to show complete results of these things. So basically that pattern is changing, rainfall patterns. We are getting the same rainfall amount within the catchment, but the rainfall pattern is shifting. We are not getting in monsoon months, we are getting in non-monsoon months. The amount is rainfall is the same. So that shifting pattern is taking place, not only within our basin, in some other catchments also within India also. So Like that, we have we have divided the entire data sets into near futures, mid futures, and far futures. So we have computed all this rainfall, surface runoff, water yield, ET. We have computed, and then once you are using some kind of a 3-4 types of GCM models and all these things, then for reaching at a particular conclusions, you require some kind of a averaging types of techniques. That averaging techniques is known as your ensembling of GCMs. So in that ensembling techniques, you combines the results of 4, 5, whatever GCMs we are using. So in my case, I simply use the mean average of all the 5 models, and I have compared that average with the historical data for both the cases, RCP 4.5 and 8.5 scenarios. So we have also computed that flow duration curves and flood frequency analysis. We have done everything we have done, and we have concluded that some kind of a rainfall shifting, as well as that evapotranspiration is also increasing in our basins, and then land use change is also taking place. So in my study area, that is the Tapi basins, initially it was 50% of area is covered by forested area. Now what we have concluded till the end of this 2020 land use maps, around 20% forested area has been reduced, and they have converted into agricultural land. So significant hydrological changes has been occurring in these basins. So like that, you can do some kind of a hydrological modelings or climate change studies. Similarly, if you have land use cover maps, like from 1970 or 85, 95, like that, temporal land use maps, you can also incorporate these maps in SWAT models. So in tutorial exercise, we'll see. I'll provide you the readily available data, that land use, soil map, everything. So you just try to run the model so that you will get the confidence. Or otherwise, what you can do, I have shown you that one India dataset portal on SWAT website. You can directly go to that, or you can download the data for your study area. So yesterday I have shared that link related to softwares. So if you have downloaded that QGIS and all these things, that is very good. Otherwise, you can download, or you just visit the SWAT website. Those who are not visited or not gone through that website, please go through that website. Everything you will get, whatever software you want, you will get. If you are working on ArcGIS, if you have licensed versions, you can go to the software folders. You will get SWAT Plus is the latest versions which they are using, or SWAT 2012 is the older versions. And then here you will get different types of SWAT Cup Plus folders, QGIS, everything you will get. Then some kind of a data set is also available, like as I've said, that India data sets for SWAT 2012. If you simply just click on that, you will get that portals which I have shown you. You can download for the entire data set, entire India. You will get the DM, entire India. You will get the land use map, soil map, even weather data. Because it is very difficult to download that NAT CDF file and that to convert NAT CDF file into the SWAT format. Because SWAT required the data in the form of text. It requires data in the raster format as well as in the text format. So you have to create the data. I'm just showing you. How you have to create the data. So like that, first I show you the weather data. You have, if you have basin means station data, then you have to create the text file for individual station. Or if you are using grid data for individual grid, you have to create a single text file like that. The first row would mention the year 2001, 01 is the month, 01 is the date, 1st January 2001 will read like that. And then the data start. Wherever it will stops, that would be the ending year, month or day of your data sets. Like that. If I have data from 2001 to 2020, so the last day means data would represent the last date of the complete data sets. ठीक है. So like that you have to create for rainfall data as well as the temperature data. You have to create like that. So this is the maximum temperature data separated by comma, minimum temperature data of the day, daily data you require. So like that you have to create single files for each stations or each grid. Then you have to create a master file. In that file you have to mention only the stations ID, their lat long values. If you have elevation, then you can mention the elevation, otherwise you can keep 00, or you can do whatever means points you have, just overlay on your DM data, or you can extract the elevation values, or you can give this. So these types of text files you have to create for your temperature data as well as the precipitation data. So while running the models, we have to provide this file. From these files it will automatically fetch all this data from this particular folder for each grid or for each station's data. So this is the format of your temperature data. Along with temperature data you need some kind of a soil data or land use data. So soil data you required in the raster format, that would be created in your GIS software, and then along with soil data or land use data you required some kind of a CSV file, that is in SWAT, that is known as your lookup table. That lookup table would contain the raster images, then the SWAT code, that 4-digit code would be there, that represents the land use class, like WATR would represent the water class, FRST represent the forest class, AGRL represent the agriculture class, URBN represent the urban class, BARR represent the barren land, RNG represent the range land, like that you have to give. And from that particular code it will fetch the information in the SWAT database. Once you download that SWAT software, QSWAT software, you will get the reference database folder. QSWAT reference 2012 for .mdb format file is there. From that files it will connect the particular land use informations. Okay, so like that you have to create a soil database also. So raster format image is there. Along with that raster image you have to create one lookup table for soil database also. So these are the code which is being used in your soil database. Since I am using the FAO soil database, so FAO soil database is by default provided in your QSWAT reference database. If you are creating your own data sets, then you have to update your user soil file in your reference database. You have to paste all this data, or you have to copy all this data, whatever you have created soil database, in your reference database. Otherwise it won't be able to run the models. Okay, if you have reservoir information, then also you can incorporate reservoir information. What are the volume of the reservoir, what are the spillway level or maximum spillway, minimum spillway levels, what are the number of gates, what types of management practices is taking place, every types of things we can do. So okay, we'll take tea break here, or after tea we'll start the exercise. So meanwhile, those who did not download or install the QGIS software, please install the QGIS software. I have already shared the link. Just you have to download the QGIS 3.4 versions. From that